Good morning, good afternoon, good evening, wherever you are. Happy learning. Let's discuss today artificial intelligence, generative artificial intelligence, and next learning in a little bit more depth. This is your professor Atif Reed Muhammad. Introduction to Generative Adversarial Network or GANs is something I would like to discuss here in a little bit more depth. GANs are a class of machine learning systems composed of two parts, a generator and a discriminator. GANs can generate new data instances that resemble the training data. Let's look into this in a little bit more depth. Imagine you are learning to make a realistic looking toy car or toy cars. You have a friend who's an expert at spotting fake toy cars. You make a toy car and your friend tells you what's wrong with it. You use that feedback to make it better, and this process continues. GANs or generative adversarial networks work in a similar way. They consist of two parts, a generator and a discriminator, that works together to create realistic looking data like images or text. In a toy car example, you are the generator. Your job is to create toy cars that are as realistic as possible. In the context of GANs, the generator is a neural network that's trained to produce new data that's similar to the training data it has been given. For instance, if it has been given a lot of pictures of cats, it'll try to create a picture of cats, a new picture technically. Discriminator, in the toy car example, your friend is the discriminator. Their job is to tell whether the toy car is real or fake. In GANs, the discriminator is another neural network that's trained to distinguish between real data and the fake data produced by the generator. It gives feedback to the generator, which helps the generator improve its creations. Let's look into deep convolutional generative adversarial networks or GCGAN. GCGAN, and let's look into an example. Now imagine you are a battery manufacturer who wants to create a high performing, safe, and long lasting battery for electric vehicles. You have a team of experts who can examine batteries and determine their quality. In this scenario, the DC GAN is your tool to help you design and create better batteries. The DC GAN has two main parts, a generator and a discriminator, as we discussed earlier. The generator is like your design and manufacturing team. The generator is a deep neural network that's trained to produce battery designs that are as close as possible to high quality batteries you already have. It starts with random noise and gradually learns to create more realistic designs. Whereas the discriminator is like the team of the battery experts, the discriminator is another deep neural network that is trained to distinguish between the real high quality battery and the fake one produced by the generator. It gives feedback to the generator, which helps the generator improve its design. Over time, the generator gets better and better at creating realistic battery designs, and discriminator gets better and better spotting at the fakes. The adversarial process helps you, the battery manufacturer, to create better and safer batteries for electric vehicles. In this way, DC GAN can be used in the domain of EV battery manufacturing to create new battery designs, optimize the existing ones, or even predict battery degradation over time. Now let's look into DC GAN architecture in a little bit depth. We'll look into the key components of the generator and discriminator, how the generator creates new images from random noise, and how the discriminator evaluates the authenticity of the generated images. So, as discussed earlier, the generator goal is to create new data, such as images, that are realistic as possible. It starts with a random noise vector as input, uses a series of hidden layers, usually convolutional transpose layers, to transform this noise into an image, and then output this fake image. The discriminator's goal is to correctly classify images as either real or fake. It takes an image as input, uses a series of convolutional layers to analyze the image, and then outputs the probability that image is real. In the context of image creation, the generator and discriminator are trained together in an adversarial process. The generator tries to create fake images that the discriminator cannot classify correctly, and the discriminator tries to correctly classify all images, whether they are real or fake. For example, if the GAN is trained to create images of cats or dogs, the generator will start with the random noise vector and try to create cat-like or dog-like image, while the discriminator will try to determine whether the image is real, a cat or dog, or fake one created by the generator. Over time, this adversarial process leads to the creation of increasingly realistic images. The DC-GAN training, how DC-GAN is trained using min-max optimization problem, where the generator tries to minimize the loss while the discriminator tries to maximize it. The importance of finding the right balance between the generator and discriminator during the training. Let's look into this together. The min-max optimization problem in DC-GAN is like a game between the generator and the discriminator. The generator is trying to create fake images that look real, and the discriminator is trying to catch the generator when it creates fake images. The training process involves improving both components, and DC-GAN's performance is evaluated periodically to ensure that it is getting better. So the min-max problem is technically the game-like situation. The training process involves alternating between improving the generator and the discriminator, and the performance of DC-GAN is evaluated periodically. So that's technically the min-max. I would suggest you to look into this in more depth in the available material on towards data science or Medium, or perhaps IEEE Explorer or Google Scholar. The examples of generated images using DC-GAN highlighting the quality and diversity of the generated samples is technically considered a DC-GAN result. Let's discuss the potential applications of DC-GAN, such as image synthesis and style transfer. Image synthesis and style transfer are two techniques used in computer vision and machine learning to generate new images. Image synthesis refers to the process of creating new images from scratch. This can be done using various techniques such as generative adversarial networks, variational autoencoders, or other deep learning models. The goal of image synthesis is to create images that are as realistic and diverse as possible. For example, a GAN trained on images of cats or dogs can generate new images of cats or dogs that look like they were taken from the real world. Style transfer, on the other hand, refers to the process of taking an existing image and modifying it to look like it was created in a different style. This can be done using various techniques such as convolutional neural networks or deep learning models. The goal of style transfer is to preserve the content of the original image while changing its appearance to match a target style. For example, a CNN trained on paintings by Van Gogh can take a photograph of the landscape and modify it to look like it was painted by Van Gogh. Both image synthesis and style transfer have many applications in fields such as art, design, entertainment, and advertising. They can be used to create new images, modify existing ones, and generate new content based on user input. However, they also raise important ethical and legal questions about the ownership, authenticity, and the use of these generative images. So let's look into WGAN GP or gradient penalty, Wasserstein GAN with gradient penalty. WGAN GP as a variant of GAN that uses a different loss function and adds to a gradient penalty term to the objective function. So let's look into how WGAN GP addresses the issues of mode collapse and vanishing gradients in traditional GANs. So let's look at an example of WGAN GP in healthcare is a generation of synthetic CT computed tomography scans from MRI, magnetic resonance imaging scans. This is an example of image-to-image translation task where the real goal is to translate an image from one modality, MRI, to another, CT, or computed tomography. CT scans are commonly used in diagnosis and treatment planning, but they can be expensive, time-consuming, and involving exposure to radiation. MRI scans, on the other hand, are non-invasive and do not involve radiation, but they may not always provide the same level of detail as CT scans. A team of researchers from University of California, San Diego and the University of Texas, Austin used WGAN GP to develop a deep learning model that can generate synthetic CT scans from MRI scans. The model was trained on a dataset of paired MRI and CT scans and was able to generate synthetic CT scans that were as realistic as accurate as real CT scans. The use of WGAN GP in this application helped to address the issues of mode collapse and vanishing gradients that are commonly encountered in traditional GANs. The Wasserstein distance-based loss function and the gradient penalty term in WGAN GP helped to stabilize the training process and improve the quality of generated images. The ability to generate synthetic CT scans from MRI scans has the potential to improve quality and efficiency of healthcare, as well as to reduce the cost and radiation exposure associated with CT scans. Moreover, this approach can be extended to other image-to-image translation tasks in healthcare, such as generation of synthetic mammograms from breast MRI scans or generation of synthetic PET or positron emission tomography scans from MRI scans. Hopefully this is helpful in understanding how WGAN GP work. So let's look into the key components of generator and the critic discriminator and how the critic evaluates the quality of generated samples using Earth mover's distance, also known as Wasserstein's distance in WGAN GP. The Earth's mover's distance is a measure of the distance between two probability distributions. It is defined as minimum amount of work required to transform one distribution into the other, whereas the work is defined as the product of the amount of mass moved and the distance it is moved. So during the training process, the generator generates batch of fake samples, and the critique or discriminator evaluates the quality of these samples by estimating the Earth mover's distance between fake samples and the real samples. The generator is then updated to minimize this distance while the critique is updated to maximize it. This adversarial process continues until the generator is able to produce samples that are indistinguishable from the real samples. Hopefully this has explained a little bit in more depth of WGAN GP architecture, use of min and max, loss optimization as well. So let's look into the WGAN GP training process. The concept of WGAN GP training process can be applied to a computer gaming example as well, where the generator is the game's AI that generates new game levels, and the critique is the game's player that evaluates the quality of the generated labels. The AI and the player are constantly improving their strategies and adapting to each other's moves, and the results of the game is an AI that is able to generate high quality game levels and player that is able to accurately evaluate their quality. So let's discuss the potential applications of WGAN GP, such as image to image translation and domain adaptation. WGAN GP has several potential applications. First one is image synthesis, which has been discussed in this lecture. Next is data augmentation, style transfer, anomaly detection, domain adaptation. So I suggest you look at these at IEEE Explorer or Google Scholar and find out more, to learn more in this area. So the conditional GAN or CGAN are the type of GAN that can generate samples conditioned on additional information such as class labels or attributes. How CGAN extends the traditional GAN framework by adding the conditioning information to both generator and discriminator. Let's look into this in an example. CGANs extend the traditional GAN framework by permitting the generator and the discriminator to be conditioned on additional information and can be used in various applications, such as inventory control, to generate synthetic and controllable data. The generator and discriminator in the CGAN are constantly improving their strategies and adapting to each other's moves, and result the game is a generator that is able to generate high quality data and a discriminator that is able to accurately evaluate its quality. So we can say that CGAN can be conditioned on a product attributes and noise vector and can be trained to generate synthetic demand data that is as close as possible to the real demand data for a store to order some of the merchandise. Hopefully this helps. Denoising diffusion models. Let's look into this in a little bit more depth. So let's look into this. The DMM can be a tool that helps to restore or enhance old or damaged photographs. The user could input a photograph that is blurry, faded, or has scratches or tears, and the DMM tool, would use a denoising diffusion model to gradually refine the photograph, removing the noise and the damage and restoring the original image. The DMM is a type of generative model that can be used to refine a noisy or incomplete input and can be applied to various fields such as image restoration and enhancement is one of them. The model works by gradually reducing the noise and refining the prediction and can be useful for businesses and individuals who want to improve the quality of their images. So how the DMMs are trained using denoising objective, where the network is trained to predict the original data from the noisy version. Let's discuss the importance of the diffusion process hyperparameters such as number of diffusion steps and the noise schedule in achieving good results for DMMs. The diffusion process hyperparameters are like the settings on a tool that helps us create new things. The noise schedule and the number of times we refine the things we are creating should be carefully chosen to balance the noise's effect and the thing's recognizability. Finding the right settings can be challenging, but it can lead to amazing and unique creations. The DDMs can be used in the areas of image restoration, music generation, text generation, drug discovery, material design, and robotics. Hopefully this has helped you understanding how the DDM works and in producing in terms of data samples and gradually refining a noisy and incomplete thing into a better shape. So let's look into what are transformers. You all have heard of GPT, Anthropic, Mistral, Gemini, and more. So I will not go into details. The generative pre-trained transformers that we will be looking into in this lecture are something that we are using now almost every day in terms of OpenAI's ChatGPT, which is the most famous. And that is technically been used in chatbots for text completion or image generation or even speaking with you as of May 2024. You might have heard of GPT-O, and that is where it speaks with you, or Hume, Hume. Look into that to expand your knowledge. Other transformer-based models. Let's have an overview on bidirectional encoder representations, or BERT, T5, text-to-text transfer transformer, and all that jazz, and a little bit more depth. So the BERT and T5 are two popular NLP models based on the transformer architecture. BERT is a pre-trained model that can be fine-tuned for a wide range of NLP tasks, while T5 is a text-to-text model that can be used to generate text from a given input text. Both models have their own strengths and weaknesses, and the choice between them depends on the specific requirements and constraints of the NLP task at hand. I would suggest you to conduct a study on this to get better understanding for you. Transformer-based models in practice. How transformer-based models are being used in practice is technically retrieval augmented generations, virtual assistants, search engines, and more. And let's discuss the challenges and limitations the transformer-based models can get and the ongoing research that is happening in a little bit more depth. The transformer-based models such as BERT and T5 and GPT, etc., or Gemini, have achieved state-of-the-art results in a wide range of natural language processing tasks. However, they also have several challenges and limitations. The first one is computational cost. The transformer-based models are computationally expensive both in terms of training and inference time. They require large amounts of data and computational resources, which can be prohibitive for many organizations and individuals. Memory consumption is another area that has a high memory consumption, which can limit the size of the models and the batch size during training. This can make it difficult to train large models on a simple machine and can require the use of distributed training. Another is overfitting, because these models can be prone to overfitting, especially when the training data is limited or noisy. This can lead to poor generalization performance and can require the use of regularization techniques such as dropout and weight decay. Last but not the least is interpretability. Since these models are considered black boxes, as their internal working and decision-making processes are difficult to understand and interpret, this can make it difficult to diagnose the correct errors and can limit the use of applications where transparency and accountabilities are important. Ongoing research into transformer-based models is focused on addressing these challenges and limitations and on improving their performance and efficiency. And here are a few. The first area is model compression, where the research is ongoing. Efficient training is another area. Explainability is coming in with a big note, where researchers are developing new methods for explaining and interpreting transformer-based models such as attention, visualization, silency, and as well as the influence functions. These methods can provide insights into model decision-making process and can help diagnose the correct errors. Multimodal learning is another area that is going on the research on a very decent note. I would suggest you to look into IEEE Explore or Google Scholar or Gemini or Mistral or Claude or OpenAI. However, keep your views to strict research basis. Thank you so much for your attention. Wish you happy learning.